landslide susceptibility map. In this figure, this region falls in the very high susceptibility class, which shows a high number of events corresponding to the high number of fatalities, and this over the Asian region. And another figure is showing the number of landslides. During showing this figure, it also clearly indicates that at the central part of Nepal Himalaya, it shows more than thousands of fatalities rate due to the landslide events, and it also shows that it corresponds to the seasonal variation. This model shows landslide risks for high mountain Asian region due to increasingly frequent and intense rainfall events. When we come to the Nepal, old study by Kathmandu shows high number of fatalities per 10 to the power 3 km square region, high fatality rate due to the landslide events. And when we see the data of YMOH from 2011 to 2021, high number of landslide events is also from the Baghmati province of central Nepal. More than 50% of cumulative threshold in terms of area occupied by the 192 number of largest landslides from this region. Similarly, 31 largest landslides occupying the 50% of cumulative landslide volume. This indicates, though limited number landslides with large area or volume have high impact. So, based on these backgrounds and following the frequency area distribution of landslide database and geological controls conceptualized by the pioneer work of Hong, I have selected this Jure landslide for analysis regarding the failure dynamics. These are the field photographs of different parts of the landslide, estimated, calculated. This shows the pressure rock in main scarp at high GSI value compared to the both flank of the landslide. Corrected, and based on that, its foliation and major joint sets are derived. Based on that, different failure modes of rock mass have been tested to show that toppling failure along the vertical plane parallel to the slope. And these are the major properties of discontinuities presented in this table. This slide shows different failure stages of landslide, where pre-failure stages are represented by the small peaks of displacement pattern that followed by the dramatic increase in displacement pattern at the time of catastrophic failure. And after then, this displacement pattern is very less, like 0. And after a few times, it has been increased, indicating to the susceptibility of landslide tanks area, as I showed in previous slide. This is a geological parameterization of model based on some lab data and field data for the numerical modeling analysis. For this study, particle finite element method application of Cat's multiphysics has been used because which is a Lagrangian based numerical approach to examine the post-failure behavior of this landslide. The Lagrangian motion caused significant mesh distortion The old meshes were discarded, and new were generated using delay triangulation and alpha-shape algorithm method. As showing in this part, this is Landsat mass. When it begins to deform, old meshes were distorted, and by using delay triangulation and alpha-shape algorithm, another new mesh were generated. In this way, it will continue until the moving mass will stop. So after that, for the to minimize the error, mesh size convergence analysis has carried out in terms of maximum runoff sediments, runoff distance, and area of affected element of the model. It shows 1 meter and 2 meter achieve optimal convergence. As I said, in this approach, mesh is continuously reforming, and during that process, volume or mass of the landslide debris change. So, to minimize the error, to optimize the change in volume variation, further computational process and remeshing process has been tested, and it shows that 1 meter and 2 meter mesh size shows optimum minimum variation. Here is the minimum variation by the 1 meter and 2 meter. The 4 meter mesh size also shows less variation, but it shows element scattering and vanishing during the simulation output. Similarly, in terms of time step convergence analysis, 0.005 and 0.0025 second time step demonstrated reasonable convergence in both computational and remeshing process. After knowing the variability due to mesh size and time step, we have done sensitivity analysis on friction angle, computational process and remeshing process. It showed 22.5 and 25 degree of runoff slope is more reliable, and it shows that the combination of friction angle at dorsal plane and runoff slope, that is 22.5 and 22.5, which we call case A later, and for case B, failure planes have 50 friction angle of failure plane 15 to 20 and runoff slope 25 are most suitable set of friction angle. Based on that, two cases were tested, and it shows different failure evolution stages in terms of their velocity. Based on that, it shows that average sediment thickness and sediment runoff distance for multilithic and monolithic bodies have very minor difference. Sediment one is smaller than the size of optimum mesh used in this simulation process, and this insignificant variation is caused due to the dominance of single rock type used in model. Otherwise, the result will be different. Based on that, this flow elevation is showing here, and as we know that this landslide caused a river damage, so we have tested for the considering static river water also. It shows different phenomena for a different case. Though there is a limited change in sediment thickness and sediment runoff distance. Based on this outputs, I have considered that influence of geotechnical, geological and structural variables are linked to the slope geometry during landslide initiation and evolution process. Friction angle of the failure and runoff planes played a critical role to determining the landslide debris volume in the river channel, similarly failure dynamics and the debris impact in the landslide area. And river water dynamics amplified the degree of impact by landslide debris within the affected area, which are highlighting the intricate interplay between geological and hydrogeological process during the river dynamics. And finally, I would like to acknowledge some key persons with the research.
Thank you. Any questions? Dr. Subodh Dhakal to chair the session, and I also request Kamal Bahadur to co-chair the session, and I request Dr. Alisma Bartola. Now, Jaya will be representative of this session. Thank you. I hand over this mic to the chairperson. Thank you.
Good afternoon, everyone. So I welcome you all in this technical session 12. Maybe many of our members of the Nepal Geological Society and other participants are highly involved in this type of work, engineering geology and geological infrastructure development. So I think this session should be more interesting. So as a first presenter, I would like to request Mr. Durga Prasad Basyal to present his paper, and the title of his paper is Young's Modulus Anastrophe of Foliated Metamorphic Rocks of Nepal Himalaya. So we have 15 minutes for the presentation and a few minutes for the question answer, because we have some more extra time for discussion. So I request Durga Prasad Basyal to present your presentation. Thank you.
Durga Prasad Basyal. I'm presenting my research on the Young's Modulus Anastrophe of the Foliated Metamorphic Rocks of Nepal Himalaya. It is on the Young's Modulus Anastrophe applications, concluding remarks, and the lastly references. Rocks types, of course there are many, but especially slate, phyllite, schist, gneiss, metamorphic, meta-sandstone, quartzite, marble. Since I'm concerning about slate, meta-sandstone, and the gneiss. The pressure orientation of the clay minerals, because of this metamorphism, of course the pressure and temperature, these are aligned along the formation plane, and this causes the anisotropy in the strength. And strength and Young's modulus are influenced, of course, definitely it is influenced by the anisotropy along the formation plane, and measurement of the anisotropy effects in the laboratory scale can be used in the development of geological, geotechnical models for foundations and structures. Of course, in Nepal, especially, we are concerning about the tunnel and foundations for the structures of their houses and everything, and definitely we have not gone for the anisotropic behaviors of the rock. That is why I'm concerning about the anisotropy and Young's modulus. I'm focusing on the Young's modulus anisotropy in this part. And of course, the Young's modulus is the property, elastic property of the materials, and which measures the elastic deformation under the stress. Well, and mathematically, it's obvious that this Hooke's law and this is anisotropic behaviors is deals with the sigma is equal to Eij times epsilon. Of course, Eij having this 36 coefficients, and they are depending upon the anisotropy of the rock materials. And then for my research, definitely it is just measuring these anisotropic behaviors for a near rock, which is slate, meta-sandstone, and then of course the granite gneiss of the Himalaya. And it is, I have drilled for the angle of loading with the foliations, 10 degree interval, 0, 10, 20, 30, 40 seconds, going for 90. And of course, the sampling, the locations, I have taken the 3 samples from the three different locations. Of course, one is the Makubesi area I have taken from the Tishtum Formation, Meta-Sandstone, and down to this head of the sections, that is the Benigard slate. I have taken these slate samples, and of course, on the lastly, at this Kodari sections, Kodari area, I have taken this banded gneiss, which is the coarse grain. So I have taken from the fine, medium to the coarse to see whether these changes or anisotropic behaves with the grain size as well as the anisotropic body of the rocks. And the research gap, of course, this is a critical research gap we do have in Nepal, and the quantitative assessment or anisotropic of the young smolars has not been researched once. Definitely in the world, there are few literature, of course, this is not more than 100 literatures are studying the research on the anisotropy. That is why in Nepal, I have not even seen one of the people have studied this, but I have seen this, I acknowledge the Pandit sir, he has put his master PhD thesis. Possibly there is some sistercity effect on the rock of Nepal Himalaya. And then to fulfill this, the consideration of the anisotropy effect constant for the engineering problems is limited. Definitely in Nepal, we are constructing lots of hydropower tunnels, especially in the metamorphic rocks, but no one is considering the anisotropic effect. And this is, of course, I will show you how these are affecting and how these are cost impact on these. And that is why to determine the anisotropic behavior of young smolars in polypid rocks under the different conditions. And of course, I have another objective is to find out whether these the anisotropic ratio is higher or less or medium or very high. So these are the objective of my research. And the method, what I have employed is the field visit. Of course, the lots of text study from the literature and so on and so on. After these things, I came in conclusion that just I have to go and field visit and sample this sampling, and then sample, prepare, and code. It is very difficult task in Nepal because this slate to core and get the core cylindrical core samples is really problematic. That is why sample preparation and coring, and then laboratory testing, and data analysis, data interpretation, and article writing and submission. Of course, this submission and data article writing so far is not done because I'm just in the first preliminary study. So, in that, I have just visualized from the literature study that I have to go for the fine grain slate to the Hetona area, and then with that there I have seen the good exposure and collected the samples and prepared for the collected samples were transported to the laboratory, which is, of course, I acknowledge the Hydro Labs Private Limited has given me the chance to do these all activities or all activities as well as the laboratory testing, because this to be transported to the Hydro Lab, and then rock sampling, of course, the suitable samples, which once we get the samples from the site and we have to analyze them whether these are suitable for the testing of UCS, because it needs some standard, and it needs this D by L by D ratio in the proper 2 or 2.5 H/STM. And then, of course, I have cored those samples from core 56.5 mm and angle between 0 to 90 in the 10-degree intervals, and then finally at least 5 samples has been cored and tested on the lab. And this process of the photograph is taken during the field visit and sampling. Of course, on the left is the sample, and second on the right is the coring activity on the in the lab. And of course, this is the samples prepared from those cores. Once we do this scoring, and then we'll go for the training, and then sample verification, and then ready for the testing. And on the right, it is the, as per my study or research, I need to put these, see those vertical or axial and diametral or radial deformations on the samples. That is why I put those strain gauges, and these are the standard strain gauges coming from this as per the requirement of ASTM. And this is the control device, which is coming from the UK, and it is manufactured in made in Italy. And it is the control device we got, and it has a 3000 kPa can be pushed up, or the compression can be done. And it is the computerized system. Once we connect those wires on the breeze, and once we model it in the lab, in the computer, and then start it, press the start button, and it will continuously record the data. And this, to do this, I have used this ASTM D7012/14E/1. This is the AS I used in my research, and this is with the medium strength variations. So this is how we measure this strength information characteristic. And the procedure, once we get the core, cylindrical core, as I explained in the sample preparation and coding, and then sticking the strain gauges, once I put those strain gauges or of course sample specimen with the 2 XII and 2 diametral or radially, strain gauges having the length and diameter ratio is 2 or 2.5, 2.5 of course, not 2 R, is placed in a loading frame as to measure its axial and radial diameters. Deformations with XL loading. So the computer, or that is the device, will record once this XL load is given, and every 0.1 second they will take the data of the XL and the radial deformation. For the Young's modulus calculations, I'm not using the radial deformations, only the XL deformation was used. So, as for the ASTM, I have analyzed these methods by 3 categories. Then we'll take a tangent and very exactly fit with those data and where it is fitting, and then we'll calculate the difference in the stress and difference in the strain, then we'll calculate the tension. Then lastly, and I can calculate this average. Once I get this elastic zone of the data, and then I can calculate the average from these formulas. On the left is for the 0 degree anisotropy, and second one is the 50 degree anisotropy, and the third one is for 90 degree. It is then calculate each and all parameters, 3 of them in a single graph, and I have come in the conclusion that while the Young's modulus with the 0 degree anisotropy, 50 degree anisotropy, and 90 degree comes with these, and shows that we do have a practice in the geotechnical investigation in a hydropower sector, and whatever, no matter the anisotropy or the layering is, then we'll go and drill the hole and get the core and test in the laboratory. And those lab data is using by the hydropower industry. So this is how, but it seems that the standard closure and the A modulus for elastic zone and then plastic zone. And from this, I have seen that always the anisotropy is behaving or is working on our data. And those data is from the literature. They are quite matched with my data, because there is a little difference, because they are putting the horizontal in 0 and I put in the 90 degree. That is why they are quite different in the nature. And from this, and discussion and this one, so the preliminary, this is current steady line in the previous instances, and each second, each tangent, and each average decreases by increasing the angle between the loading and the anisotropy plane. So, challenge, of course, we have instrumental challenge, logistic challenge, application challenge, and economic challenge. These are the very challenges we are facing in the industries. Of course, especially we have to drill, and we cannot drill in the proper alignment of the edge for the 90 degree or 0 degree. That is why we have to consider those challenges. And the application, of course, this is the application that we have done. Seen the tunnel deformation prediction that definitely we will use. If we use the anisotropy values, and this tunnel prediction will be verified. And of course, this compression control, such response modeling, numerical modeling, of course, the RS2E, especially now hydropower industry or tunnel is using tremendously there, and we are fitting these e-models values. Of course, that is, we have to consider rock support design, hydrofracturing guidelines, and loss-prone deformation as well. And the concluding remarks, it is very preliminary because I have not completed so far all the test values. And what the preliminary data shows, the data analysis indicated that the strong anisotropic effects due to coalition orientations is there. So be in mind that whatever we are getting from the lab, whatever the report coming from this drilling activity is not correct, we have to use or we have to think about the anisotropic effect of the. And the Young's model definitely decreases by more than 50%. That is only the calculated data. I have not definitely say that this is the valid data because I have to input the data. I think that possibly it will be okay or it will be revalidated. And then results, limited results data highlights the critical role of anisotropic in underground design and stability. That is why it is concluded that we have to think about while designing the underground activities or underground tunnels or the stability of the ground or tunnels. And of course, this is the remarks, and thank you very much.
The initial phase of your PhD, so it is nice to give some feedback to you. Anisotropy is very important, of course, and when you do this E-modulus testing, also at the end you do also UCS. So that is important. And another is always remember that minimum minimum E-modulus and strength will be around 25 to 35 degree range. So you have used 0, 50 and 90. 90 is parallel and therefore it is smallest now. So then you should do more, you should give more focus between 20 to 35 degree.
Actually, I have data, sir. 0, 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, 60, 70, 80, 90. Altogether I have data, but in this initial stage I have just calculated the 3 numbers. That is why I presented this as preliminary. That is why I just wrote in this is preliminary field or preliminary stage.
Here also if you should have shown with this around 30 degrees, so then audience would have got some information about it.
Yeah.
Mostly it is 35 degree, the lowest value will come. Okay? So then you should follow his research in future. So that it's a very good work and you should collect all these lesser Himalayan rocks and do a good job. And then another recommendation is when you put 0 degree, instead of writing 0 degree, perpendicular to foliation and parallel to foliation. Then it will be much easy for others to follow. Okay? Thank you.
Our idea is to develop a relationship with any matter, no matter what direction you are taking the samples, then mathematical relations which you will feed on it, well, then get some sort of data or Young's modulus, which is not dependent on the collision or anisotropy. So, in this case, of course, now these data, anisotropic data, should be included or should be considered as I put in the applications. Well, all the RS2 designer and of course the rock science designer or other finite element designers are using Young's modulus Poisson's ratio as well as the strength parameters. They are not considering the anisotropic effect. And I've read in literature some of the cell that is conducted in US and the other countries, in China as well. There are the anisotropic ratio varies from 4 to till 10. It means that it is tremendous effect on the engineering design. If you are putting these conservative values and you will be end up with the conservative support design, which you will give the contractors or the consultant the huge economic values, which you can, if you put these anisotrophic behaviors or anisotrophic parameters on your design software, you will end up with a very good this one. So you can use that one and consider those parameters. And it can be used with this all of them.
The slope stability analysis using continuous slope mass rating along the cantilever from 3 Banjang to 4 Banjang by rock function. The influence of geomechanical structure and variable rock mass parameters in slope stability study. Mr. Sandeep Reddy, please go ahead.
Actually, this is my privilege to give presentation regards to the influence of geomechanical structures and variable rock mass parameters slope stability. First of all, I want to introduce myself. First of all, introduction. Actually, slope stability of rock mass is influenced by pattern. Actually, it's a complex interplay of geological factors like integration of the rock, type, properties, and this orientation of the discontinuity or addition to the geometry. In addition, the geometry of the slope, groundwater condition, and salinity of the area is the inseparable slope stability of the rock mass. Actually, the influence of rock mass and slope stability is actually vital, and actually it makes the, in addition, there is a uncertainty in geological mass and variable rock mass properties. It is furthermore found. There is a circular failure sloping like this. If in this block there rock mass, if it realizes this slope direction is there is waste failure, and there is if the point plane realizes the slope is plane failure, and top plane failure is quite complex. It's actually opposite, and so in block failure assessment it's also taken as complex line failure. And there are two types slope stabilization is a empirical kinetic equilibrium and numerical model. There are four methods. And rock mass parameter for especially slope assessment are described by millimeters like RMR, SMR, continuous slope mass that my one also presented for this, and so geological strength index and new slope and more this. And the time they take spacing and condition, intact rock strength, RPV, groundwater, orientation of the line, distribution of rock mass, slope angle, excavation methods, and slope height. What all the methods categorize all these parameters. So if you quantify slope stability from one method, it does not give true results, or it may not be valid. Just like only in all parameters, especially not discontinuity plane, only is taken by out of 40, only 40, and the maximum actually is the maximum. And by condition taken by 30 and intact rock mass system by 11, RPV by 11, groundwater by 8, and slope height. Most of them only 7 use slope height, because slope stability assessment. I take these sources from calculators and my objective is that to understand the impact of geomechanical structure on slope stability and to examine the influence of variable rock mass parameters. Both sides. And the study area actually now I am working with two specific studies, and it lies in 3 districts. Kota, Kathmandu, and the 30 meter high, and this is the green line. Sorry, blue line is the reservoir storage at 640 meter elevation under that conception, and this is the 13 kilometer headwater tunnel. And it's calculating the type of dam is actually CFR dam and that distance is and light and then if we talk about reason observation, and it's like and here's the rock, it's like steady formation. In the rock, we get quartz actinolite, the quartz actinolite, and most important structure is there are the HCG, which they get 15 kilometers, and there are MEG, there is 30 more than 15 kilometers. And that site is, as I already said, setting condition. And this is the geological map of by Vikas, and it shows the detail on this. Actually, there's a linear density map that I did from the project study done by myself, and we could see the pink line, small pink line is actually dynamic here, and it is blue color is the reservoir as I already said. And second one, this is a dynamic density map. In the near from the Redox to from that to about the bit of the electrons, there is a high density of the dynamic. And here, this is a sporting collar, and this is a dam, and this one is dam axis, and this is a rock of Jutkoshi, and there is a rock of collar, and there is a dam, and you could see that there is a linear, this, and this, and here is the photo that shows this photo. There you could see the geomorphological evidence of dynamic tropical area. And there is a geo-water study that's conducted in the area. Here is the GM, here the location of the hydro project in the area, and there is also landslide. Red color is the landslide. And there are three main types of projects in the stable areas are identified. Landslide 50. The reservoir area 60 that is located in one particular right bank, and there is 50 plus erosional areas. And the red one is this, and these are the landslides. And actually, this inside is very on the margin of just like the kilometer opposite from the dam axis, where this inside study conducted by my supervisor at the university, and there it shows that the 2 points are taken from inside study, and it shows 15 kilometer displacement is 130, so in 1 year. And this is the geological and geotechnical information of nearly more than 20 borehole are drilled and 24 borehole are drilled, and about 2 kilometers are drilled in this brilliant and drilled in the redox area, and these are the geomechanical stations that the project study. And I myself take study on this area. For my studies, I also done some few works. results of my study. This Armimer value, on the right, this Armimer value, GSI value, precious value, and arbitrary value of the right bank of the dam. We could see the right bank dam is paired off is shown in GSI, Armimer, and its USS value has more higher from 100 to 150, and RPD, but RPD is quite low in comparison. It's a 4. And if you compare with left bank, you could see it's a rock mass by failure. Here, very good rock. You could see in GSI, and gives its value is high from rock is more. RPD also, you could see very good rock. The left bank. And these are the material properties that I have already described. I analyzed the answer for precision strain, and this maximum, minimum value, and standard deviation of them. We could see that there is a maximum standard deviation, 47.4 in answer for precision strain. It's taken by the speed handler. And the RPD is standard deviation is 28. And joint number is there is 3 set joints, but there are also few random joints plus 3 joints plus 1 is out in some places. Spacing is 2 to 6 meters. Consistency is 1 to 3 meters. Aperture 1 to 5 meters. And you can see the planar rock. The rock type is quartzite area. Rock type quartzite is slightly weathered and it's blocky, but in boron drilling, you could see the texture of mass, and the groundwater is really dry, and the mean Armimer value is 62.7, is quite good, and GSI value is 61.30, this was quite good in left hand, and this is then the right hand, this is K-line, and GSS value, GSS value is 117.8 UT. RPD is minimum, maximum 85, and minimum is 5. Statistical matter. What is random 0 to 25 and spacing to up to 32 meters, 6 meters. Consistency is nearly same. And this Armimer value is 52.5, little is less than left bank, and GSI value is also less. And this is the dynamic analysis of the right bank. You could see it's a weight analysis. There is a preset condition, and this natural slope. And this is the mode of failure of the slope and height. Here is the failure percentage, and here is the slope angle. And blue color shows the waste failure. When slope angle increases, and the failure percentage is also. And plane failure is this one is plane failure. This one is topping failure. Even in increasing slope angle, the topping failure does not increase in this chart. And when you see this chart, this is the failure percentage, and this is the friction angle. Increasing friction angle, it shows where is similar value. What increasing friction angle, waste failure percentage decreases, because it means that not only friction angle, other parameters also play a role in the slope distribution. This nearly straight line shows. And also the weight and plane failure also determined by orientation. It may be also the drag factor, slope angle, and orientation of this one. And this is the dynamic analysis on left bank. And this is here I also conducted failure percentage and slope angle. Slope angle, all the ways failure are counted failure percentage. And mode of failure, I take mode of failure for slope angle 60 degree, and there is a fixed angle and there is a failure percentage. Here it shows the plus failure 90 degrees while the fixed angle of 26 to 35 is the fixed angle to engaging to fix an angle by 2 degrees. Taken there. And this is my conclusion. Impact of geomechanical structure. Geomechanical structure like fault dynamic reduces RPM, RMS, and GSI. Slope failure shows in blocky rock mass because this is determined by structural orientation and also fixed angle also play a role on this. And disintegrated rock mass failure is complex or circular shape. And we should not forget previously on the right hand of particular and slope displacement is marginal, which is their way, which is obviously marginal from that axis. And influence of rock mass parameter on slope stability. Slope stability depends on rock mass like RPD, right surface, rock stability. Up in parameters in the slope stability like RMR and slope. Actually, this is my limitation of the study. I do not calculate the slope, and I have got numerical modeling. Only probabilistic analysis is considered. And actually, the heterogeneity of rock mass parameters observed in the study and the standard deviation is up to such 40 in standard deviation. For usage state, parameters should also be considered in addition to friction and slope for distribution of system. That is my further class. And actually, we could take it the limitation of this.
Thank you, Sanjay, very much for your nice presentation. We have 2 questions.
Phyllite.
In the right line, there's phyllite occurrence, and in the chart, you have shown that there is no changes in the toppling failure as the slope rises. What could be the possible reasons for that?
Sorry. No, not only for toppling, you should, it is determined by slope angle and slope direction, and the joint angle and joint direction. Yeah? So, toppling is determined not by rock type, but also, but in friction angle also play a role on this.
Yes.
No. Because the joint discontinuity that I have plotted might not be within the range of toppling or plane failure. Other rock joint that I have plotted, there are nearly 81 holes over there. Yeah, it might not be lie within the failure range.
How did you differentiate the geomechanical and geomorphological side?
Geomorphology means geological features that hill slope. Actually, we could in engineering terminology, we could also say that it's an engineering geometry of the hill. Yeah, geometry of the hill slope, geometry of the landscape. But geomechanical parametric structure means joint discontinuities.
Do you produce the geomorphological also?
No. I have taken from in this study I have measures joint orientation, joint geomechanical properties also. I have the data that I have taken from my you could state is a study and taken from others. Geomorphological that I have taken. Just aerial photo interpretation, satellite interpretation.
Do you prefer to first the geomorphological or geomechanical?
Both play the roles. Yeah, as that I described geometry height. Actually, in the slope stability, height of the slope play the important
slope angle, height of the slope play the main role that I have already said. Some of the classifications do not consider the slope height.
You are considering the local geomorphological across the whole area.
Yeah. For this, we could have another measure, just like we could use satellite image, and just like hazard mapping, we could say probabilistic measures. That's parameters we could identify from this estimate.
Thank you. Thank you, Mr. Sanjeev Reddy. You can continue your discussion outside in the foyer.
We can do it after this presentation is over. Now I would like to request another presenter, and the title of the presentation is Recognizing Deep-Seated Gravitational Slope Deformations around the dam and reservoir reef surrounding area of polygonal river basin. And the authors are Narayan Gopal Khide, Ranjan Kumar Dahal, and Lal Prasad Paudel. And I request Narayan Gopal Khide to present this this research. Okay, thank you.
About the DGST, deep-seated gravitational deep-seated gravitational slope deformations. This term, many people may not know about the term DGST, deep-seated gravitational slope deformations, and in some cases it's confused with the deep-seated landslide, large-scale landslides too. And so I try to differentiate what is DGST and what is the deep-seated or large-scale landslides here. My story is mainly from the geomorphological. What is DGST, deep-seated gravitational slope deformation? Is a preparatory process linked to deep-seated gravitational process. Is the preparatory process of the further large-scale landslides. It's a process. It's a phenomenon. Deep-seated gravitational slope deformation is a phenomenon that is a preparatory process for large-scale landslides. It's have been studied since 1960s, but in the Himalaya, we seldom found the documents or literatures about this matter. But in the Alps and other mountain regions, there are many more papers and literatures, scientific articles are there. Mostly in the, I use reorganize to hear about these topics. And there are some definitions of the deep-seated gravitational definitions. One definition is by Goriated 1940, scale landslides by Hasegawa 2009. These are the major features of DGST rather than deep-seated landslides. The main features are the multiple scarps, tension cracks of the multiple level, in the multiple level, and double breakage, etc. And mainly in the DGST, in the case of DGST, it's rather than in large-scale landslides. The lower reaches of the polygonal region, there is a proposed design, not proposed, it's a design hydropower project, IDAM project, that is polygonal IDAM project. In this area, I am trying to find some DGST masses that could be transformed into the catastrophic landslides after filling the reservoir due to the percolation of water. So this yellow region is the catchment around the within and around the reservoir area. It means the FSL goes up to this point. There are two major streams, Agukola and Burikandaki River. The full supply level of the reservoir is up to these points. So I am trying to find some DGSD masses, some DGSD masses within this area mainly. Before study and analysis around here, but I find some of the DGSD masses over there covering the basin. Then I narrow down to the within the reservoir range. This is the geological setting of the area. This is geology of this area. Here is this. This is a point of dam site. It's a dam. A small black cross across the river. In the black colored, it's a quartzite exactly, quartzite band. There is a dam, and the opposite is the reservoir area here. And the geology of this area is like this. It's based on sloping and buttress. The same geology over there, geology of the area. These are the features of deep state gravitational slope deformations. These features. Yes. These are the features, and we can see the multiple discards, multiple failure there. In case of landslides, we can say this is one landslide, or maybe initiating the landslide was initiated first from this part, and then again this evolved like this. Another scarp is here. The next failure is here. Next deformation exactly. Deformation in the rock. And next is here. It's the most multiple scars you can find there. And these are the features seen over the DGSD area. This is main topic because I try to differentiate large scale landslide and deep state gravitational slope deformations. Based on these criteria, these parameters, there, genesis, deep state gravitational deformation, the genesis of large scale landslides, and movement rate. It's a movement rate of the DGSD is very slow in the scale of millimeter per year, and the landslides very rapid. In case of creeping, that can be slow, but very fast compared to the DGSD. And deformation features, some deformation features can be seen in the field. These features I can observe in my field study area, and these features can be seen over there. And failure mechanism, it's a progressive and very slow, evolving slow and progressive. And this is sudden collapse and triggered by secondary process. Depth of movement. The depth of movement of DGSD, deep-seated gravitational slope deformation, is more than 50 to 100 meters or more, and evolving in time mountain ranges. But In the case of these large-scale landslides, then maybe SAP too. Triggering factors. There are some triggering factors: tectonic activity, and long-term river incision uplift. Uplift due to river incision, rock mass strength variations, and in case of landslides, earthquake, intense rainfall, river undercutting, human activity, etc. I cannot find any evidence relating with the human activities in the case of DSTs in literatures. And evolution. Evolution. The evolution of DST is very slow. Very slow evolution, and it's rapid. These are the major differentiation of the landslide, large-scale landslide, and DSTs. This is model taken from the Asagawa et al. in 2009. These models are coupled with the deep-seated landslide as well as to the DGST masses. These are in our case. This land mass is completely moved land mass. This is the DGST mass. The dense populated area, this area is settlement here, is Lapland Hills. That was severely triggered due to the 2015 earthquake. And at that time, the total village was evacuated from this point to the upper part. There is some flat area, and they go there. And this is a mapping, scales map of the DGST mass, DGST area. We can find some feature like this. Our Himalayan landscape is like this, and this is a DGST mass.
Okay, so you have 3 minutes more.
This is DGST mass over here. Then we can find other cases too. This is only an example. These are some examples of the DGST mass and triggered by earthquake. This is my work, and I'm finding some DGST masses over here in this area, in this basin, Kurikandagi basin. Then this part is reservoir area. This part, Kurikandagi area reservoir is here, and we can find number of DGST masses there. Some are outside of the reservoir level, then some are around and at and within the reservoir too. Here you can see the reservoir basin is here, and I can find more over there. Here you can see some DGSTs are within the reservoir. While the reservoir is filled after building a dam there, and some DGST masses maybe within the reservoir. This is the case, and I try to find the impact of the reservoir water by percolating to the ground and filling this reservoir. Then the scenario could be catastrophic. This is attribute of the DGST masses. The number DGST coding here, DGST number in the year, area, it's and the same. You can find. These are the DGST. Find over there is basic. The recognizing DGST in the Himalaya, I already mentioned, it is based mainly on the geomorphic analysis, geomorphic features observed in the field. Some key indicators of the DGSTs we can observe over here in the field. This is in my study area, from my study area. These are some cases and some data informations I picked, observed over there. The role of external factor to the DGST basis. What could be the scenario? I try to explain over there. There are some examples of used DGST masses, and these are the these also. Comparing to the previous one, we can find this whole village area was some years before, many years before, maybe slipped down to here. This is the DGST mass. This is also a DGST mass. Here you can see the mass slip over there, and the thick DGST mass is here, and it's pressing the river terrace or villages to the river. Our infrastructure development maybe within this DGST mass sometimes.
So can you summarize?
Yeah. These are the DGST mapping in the field, and these are some examples of DGST mass. This is a terrain analysis. That's why I can find and recognize the DGST in my area. Thank you.
Okay, thank you, Priority, for the further research, and you have done a nice presentation.
Yes.
There is a data storage age of 50 years, presumably. Generally, that is the practice. And you identified numerous deep-seated slope deformations around the reservoir area. So, what is your finding regarding if there is construction of dams and there is a daily fluctuation of water levels? Then the presence of those slope deformations, in how much way in timeline, in terms of timeline, will affect the data storage that is assumed to be of 50 years.
And now it's a continuing project while completing my PhD. Then so that in next phase, I go through the individual DGST there. First, in this next phase, I classify the DGSTs over there, in and around the reservoir. Then I analyze the most critical DGSTs which severely impact into the reservoir. Then I can draw some conclusions over there. Thank you.
It's very difficult to answer. I am also a geomorphologist at the Geological. As you are trying to do PhD, what is in your mind?
Individual DGSTs over there. Then already I mentioned to the answer previous commenter, and I could find some reason. But in this area, the slope is both bank slope is not so steep around the reservoir. The slope is very gentle slope. I mentioned here only the mass deformed due to previous tectonic or other gravitational processes. So this time I am not able to answer your program.
Okay, thank you, Narasar. It will be better if you can, for example, monitor some of the DGPS you are trying to find out, you have already found. So if you can track them with some instrumentation. This is just my question related to not only to your PhD, but for future also. So in that case, your results will be more refined and more validated. So that is one of the question, and maybe some of the old landslides, they may undergo, as you said, deep-seated deformations again. So maybe that also needs to be studied in future. So that is my quick observation related to your research. But otherwise, I found that this research is very, practical, and we need to, do a lot of this type of research. So thank you so much for your presentation. Now, now we go for another presentation, and this presentation, the title of the presentation is Implementation of TBM Tunneling Project in Nepal Himalaya, and presenter is Ajay Raj Adhikari, and of course there are two authors, Ajay Raj Adhikari and Chunavar Roli, but the presentation will be done by Ajay Raj Adhikari. So Ajay, please start your presentation.
To start with, whether to build your tunnel with the TBM or not, then you start with the accessibility. You know the accessibility situation of the country, the road, then the carrying capacity of the road and bridges in Nepal. If your tunnel is more than 5 meter diameter, let's say, then your quarter is coming up with more than 85 tons, 85 metric tons. So the road capacity, the class A road capacity is limited to around 18 ton axle load, right? So if you have 85 ton in a single container, you have to have more than 5 axles in it. So based on that, you choose accessibility. Then what is your geological and geotechnical condition along the tunnel line? So are these geotechnical and geological conditions favorable to the TBM or not? Then you look at the length of the tunnel, because the cost of the tunnel, it is directly proportional to the length. So if your length is going to be very big, and from the single orbit you need to dig more than like 5-6 kilometers of tunnel, then there are various methods that can be better than the conventional drilling and blasting method. Then availability of edit itself, I mentioned earlier. So if you don't have edit and you are going more than 5-6 kilometers from a single phase, then you have to think of, rather than adopting some conventional methods, why don't you go for other mechanized excavations, maybe road error or TBM. Then where does the tunnel, the construction of tunnel lies in the project schedule? Is it in a critical path, or you have plenty of time to build the tunnel? So it also depends on where it stands in your schedule. So while choosing the TBM, then roughly we have a rough idea that how much tunnel we can make with the TBM in a single day. This is the model prepared by the Colorado School of Mines. We say CSM model. If you look into it, the rate ROP stands for rate of penetration, and this is the blue line. The thrust is the thrust of the machine. The red line is the cut rate power. So if you look at this blue line, then the rate of penetration after 150 MPa is relatively low. You can see that we can make 3 meters per hour, but the actual progress of the tunnel is less than 50% of this rate, because you have to spare the same time for the machine maintenance. If you have the cutters, then it gets wear. You have the hydraulic system, you have to repair it, you have to fuel it. So the actual production will be less than 50% of what we can see the rate of penetration here, right? So when the UCS strength of the rock is more than 150 meters, then it's better not to choose TBM. If you do it TBM, if you do it conventional drilling blast, then you can have a more pull, rock is more brittle, you can have fractures, you can get it done, right? With the TBM, what happens is the progress is slow,
then you have to replace the quarters quite often, and replacing one quarter will take more than half an hour. So if you have 40, 50 quarters in a TBM, then if you need to replace 4 or 5 quarters in a single day, then that will take 3-4 hours. And you have additional operation hours in that, right? So how much tunnel you can make in a day is quite less than what we could have done by conventional method. Then this is the example of Very Babai. So how did we end up with choosing the TBM in Very Babai is, so this is the outlet portal, we say like inlet outlet portal of the tunnel. It was around 309. So 310 meter, outlet portal was in 310 meter, and the inlet portal was located around 455 meter elevation, right? So if you move all around the tunnel, nearby places, there is no way that you can get the elevation lower than 455 meter. So there was only one possibility of audit. And if you started digging audit from here, the length of the audit was coming around more than 2 kilometers, and that was in negative slope of 1:10. You can imagine the digging of tunnel 2 kilometers long in a Shivali with negative slope. That itself is a big project and big challenge. And that helped us to decide why don't we go with TBM. Right? And that was the reason that pushed us to use TBM in Very Babai project. So for rough study during pre-feasibility or even feasibility, what you can do is like you can use those graphs. This is prepared by Atlas Copco based on the TBM performances and cost of the tunnels. If you look at here, if your tunnel is very short, let's say 400, 500 meters, the cost of TBM, the yellow line, the cost of TBM is going to be very high. So when it comes to 1.5 meter to 4.5 meter, it depends on so many factors. The geology, the geometry, the environment, and project timelines, right? So why geometry is important is that with TBM generally we make circular tunnel. You don't have the flexibility to change the tunnel into other shapes. You can do it for sure, but it needs money, right? So you have to fill the curvatures and make it flat if you are trying to have the horseshoe-shaped tunnel or other shape of tunnel. Then you can see the 3 kilometer is a break-even line, I have to say. So if it's shorter than 3 kilometer, 1.5 kilometer, don't think about TBM. It's much cheaper with other methods. So if it's between 1.5 to 4.5 kilometer, you can think of TBM. You have additional financial cost, right? The yellow line is coming down, and this is with the TBM. So if the tunnel is more than 4.5 kilometer long, then the TBM is getting beneficial. So this is the, it depends on project as well, how much return you are getting from the project. And if you reduce the construction time by 1 year, maybe you will be making more than double of the TBM price itself. Then why don't you go for TBM? Depends on other factor. But in general, you can refer this graph to choose whether to go with TBM or other methods. Then once those things are done, then you prepare the TBM design, then general study, then you have the phase condition, response of rock mass when excavated, how does the rock mass responses to the excavation, pressure the TBM has to bear when it goes along this line. Road error, in other methods of tunneling, NATM, we do that. Rock mass characterization is always there. Then you have to have a progress rate. Because the investment and the power consumed by the TBM is quite high. So if your progress rate is coming too low, then because of other ancillary costs, that is not directly related to the tunneling and support system, the cost of tunnel can be very high. So you have to think of progress rate. So how fast I am finishing the tunnel if I am using TBM. Tunneling, in others tunneling also, because the contractor will be based on, when contractor bids the tunnel, then they will bid based on this one. So what are your investigation report that will be reflected in geotechnical data report? Whatever investigation you have made, whatever test you have done, that's not in practice in Nepal these days. So geotechnical interpretative report is the property of the employer, right? So this interpretative report is your interpretation of the ground condition. It's not the contractor's interpretation, right? Because the contractor, it can be national or international, they might not have worked in the tunnel before, it could be like that. So they will take the interpretation from our side. So what our ground, it means like the employer should know the ground better than other parties. So they think that the interpretation from the employer can be better. They read this, then they make their own assessment, right? Because they are the construction experts. So if this is the ground condition, then maybe I will just retailer my construction ways and I will get money out of that. So this is the report, it's very important, but it won't be contractually binding.
So you have 3 more minutes.
Because it's your opinion. These are the general things we do, and based on the ground condition, it can be found in internet as well these days. The information is very easy. So based on your ground condition, you choose the type of TBM, which type of TBM you are going to use, right? The main beam, or single seal, double seal, hybrid, out pressure balance machine, solid sheet machine. These are just the examples that I have shown. And these days, what the technology has been moved very fast, and if you want something else that is not in other TBM, and you pay for that, then you can have those features in your TBM. These are the existing ones I'm sharing, and if you want to have something extra that can handle your ground well, then definitely it can be built into your TBM. Right? So it's an assembly of many machines, and you can have 1 or 2 machines in it. If there is no seal, then we don't have to think about that. The TBM thrust, based on your rock characteristic, how much energy you need to cut that part of the rock, and how much specific energy you need to shatter that rock. Based on that, you choose the TBM thrust, TBM power, cutter head characteristics, cutter type and materials. So like we are choosing the drilling bit for different formation materials in drilling the well. Similarly, we choose here the cutter types, cutter materials, characteristics. So it's very simple and like a drilling machine. Big and horizontal drilling machine. Then after this TBM design things are done, then you go in the contract procurement things, you fix the procurement, and just want to highlight some ancillary facilities that you can have these days in the TBM. This is the example of the camera in the face of the TBM. So new mechanized tunneling interventions. So if you have the camera in the cutter of the TBM, then the rock shattered by the TBM, it was showing the concentric circles like this. And there was a small clay spot, you can say, and that was recorded by like this in camera. So if you have a camera in the front of the TBM, then you don't have to do anything. You sit in the console, operator console, you get everything. And this is another example. Then another thing very important is like how do you handle the risk, and which risk is being borne by who? The employer, consultant, or contractor. This is very important in making a TBM tunnel a success. So who is responsible for unforeseeable ground condition, machine breakdown and repair, over excavation, and consequent changes in the cost? You know, like maybe you need 200 kilonewton, but he is imparting 500 kilonewton into the ground. Then you could set up the whole ground. Rather than tunnel, you have a cave, right? You need money to fill that cave, then who will bear that risk? Investigation, finding, during implementation, right? So, like all machines, TBM also have a learning curve, right? They learn from the ground for first 2-3 months. Then based on that, they operate. The operator will operate, right? So during this learning curves, what are the findings and how you are going to use those findings in the further implementation of the tunnel? Then progress rate versus payment. And this is generally we expect in the ground that the rock is very good. Right? It's quite different. So these are the general things that you need to take care of while you prepare the TBM tunneling and implement it. And contract types can be item rate, design build, camera group. That is new to us, but some of the companies from ENEA, they are practicing this for the first time, I guess. Get to see like how does it work. Then EPC contract, additional document, additional risk allocation, then financial alignment. Arrangement is very important because in the very beginning you need to invest lots of money. The TBM itself costs more than $1 billion, right? So that will require a huge investment in the beginning. Then how is the cash flow status of your company? You need to take care of those things. Then advance payment to cover the cost of the TBM logistics. You have to have all the quarters and repairs in the site, right? That has to be brought for like 2-3 months. And if something goes wrong, then you have to, rather than stopping the TBM, it's better to pay the contractor some advance that he can bring all the necessary arrangements, he can make necessary arrangements. Then you have high capacity cranes, more than 135 tons, provisional sum for unlikely risk. Fixing the payment mechanism itself is a challenge. Then design finalization.
Okay, can you summarize?
Yeah. Then one thing, I'm done. So one thing we have to take care is like, you in design, you assume that my TBM will do this and that, those problems will be handled by the TBM, but when contractor submits the design of the TBM, then you end up with something that you cannot predict now, and at the middle of the tunnel you found it. Right? So you have to be really careful on that. Then with that, proper planning with supplementary additional studies, right use of tunneling technology, a prepared machine with adequate facilities, risk allocation methods, the TBM tunneling can be a success story. Thank you.
Okay. Please show this graph which you showed us with respect to kilometer and cost. This graph from where?
Atlas Copco.
I disagree with this graph because any TBM that is short, any tunnel that is shorter than 10 kilometers, it will never compete with drill and blast. So if it is more than 10 kilometers, only TBM may compete with drill and blast. In this also in condition that there is no income. And another thing is that the cost and the length are also dependent on what type of TBM it is. So if it is a Grico TBM, it may compete with drill and blast, but the shielded TBM, they are simply too expensive because of the concrete elements to be installed, and then the blast needs to be placed and then grouted. So it will be at least 2.5 to 3 times costlier than drill and blast. So you have that experience. So you should have compared your heavy and TBM burst. This is my comment. Thank you.
Okay, thank you, sir. Thank you. It definitely depends on type of TBM and what facilities you are having in TBM. And with double seal machine also, it is possible that we don't erect the segments, because you can take the reaction from the ground and move forward if your ground is very good and you're comfortable with it. And definitely this might have negative implications as well. Depends on the project cost and the limitation and how much money you are making out of the tunnel. That also depends on this. But I think that they have considered more than 130 TBM tunneling projects and compared the cost, and based on that they found this graph, right? And our project, let's say like there are other projects which are 5 kilometer long in year, and we have 10-13 kilometer long tunnel. We have compared the cost. Definitely, if it's not in the critical path of the project, then you can go with TBM for sure, right? But if it's in a critical path, then making more than 30 meters in a day from 2 phases is next to impossible. It's next to impossible, right? So based on that, we have to choose whether we are going for TBM or other methods. Right? This will give you just a rough idea. It's not like, okay, you have to go with TBM, it's more than 4.5 kilometers, or go with drill and blast when it's less than 1.5 kilometers, right? These days, the metro tunnels, 500, 400 meters long, they are going with TBM. Even the EPB machine, that's more costlier to handle as compared to the double seal machines, right? So why they are doing that is because they are making money out of it. They don't have the manpower, right? And it is safer. So there are several other reasons. That can be compared with which method of tunneling we are going through. So based on that, we have to make decisions, and this is just for reference, and you have a rough idea. Thank you, sir.
Okay, thank you, Ali. Now,
my concern is just to know whether you have all the information, baseline geotechnical report, and what you observe in experience. And so just you go with your first slide. Design report is there, and your baseline geological report is there. Have you collected this GIR?
No, GIR we prepared.
You prepared?
Yeah, we prepared.
Okay.
That's not in practice in Nepal so far, I guess. GBR we have prepared and given it to the contractor. GIR we haven't practiced, but it's better to give.
Yeah. My concern is if you have finished, because your project has already finished.
No, we have the as-built. Definitely, we have the as-built geological map, drawings, and geotechnical information. Yes, we have. We have.
Because my concern is that what is your ground characteristics and how your machine is going. And so what thrust you are applying, what is your configuration of the blade, that I'd like to know.
Yeah, that we have.
That is a part of the research.
Yeah, we have.
And what will be the future in Nepal? What will be the future of this TBM in Nepal? Okay.
Thank you. So based on the learning from Beribabai, we did the TBM tunneling in Sunkoshimari. And now we have 2 learnings. So we are growing rich with those learnings. And definitely it will be rather while comparing with the Beribabai, Panti sir is here. And we talked in one of the NTA conference, I guess. Then Panti sir, he was telling me that maybe this is the first time you might end up with some trouble in the middle of the tunnel. That we were very scared, but we did it. And with that learning, we improvised our doings in Sunkoshimari. So now we have 2 learnings, and with those learnings, the NA engineering, they have started studying the possibility of TBM in other projects. In some of the companies, Sanjeev is here, they are already going with the TBM, right? Based on those learnings. If you have more learnings, then you will grow more rich. Then your learnings becomes more effective, and it will be cost effective. You get the ideas of cutting down the cost within the TBM itself, and how do you make your project better, the durable. So those things comes up with more and more learning. And projects, what we have been doing with TBM, we have project completion report, all those TBM thrust, torque, rotation and machine, the cutter chain, all data are there. And based on that, we are learning.
So that's why I should give her for one question.
You have mentioned all conditions to be used for TBM. So I have got questions about, have you faced any problem when TBM encountered a deformed zone, shear zone? So if yes, could you share us how it was resolved in that time?
Many times. Many times we have faced, right? In India, the TBM has not been that successful because those things, those geological surprises were not built into the contract itself. If your contract cannot show you a way that how do you move forward in the adverse geological conditions, then you cannot do anything. The challenges we faced in Sunkoshimari itself, we have more than 6 stocks, TBM stock. In Beribabai, there were 3 stocks, right? So what solution we did was, sometime you can improve the ground, you can treat the ground ahead of phase, you can walk your TBM. That's the one way out. If you get to know the problem before you go through those jobs, right? And when TBM gets stuck, the only thing you can do is you can make a bypass tunnel. So you cut into the seat of the TBM, then make a tunnel from the side of the TBM, and move forward, release the face, and you make a bigger tunnel. Then you stabilize the ground ahead of the face, then you walk your TBM. And we have done that in Sunkoshimari. We did it more than 4 times, I guess, bypass tunnel. 4 times. In Sunkoshimari we made it 4 times. In Beribabai we did it twice. Thank you.
Okay, thank you, Ajay. So nice presentation. So as for this schedule, we have the tea break from 16 to 16:15. But according to the organizers, they said that this tea break is already not in the schedule. So before that, the next technical session will be started. So I request if the chair and co-chair and the reporters are here, and of course the presenters of the next session. So I request you to be prepared for that. After that, still some announcement of these vehicles. Gravity analysis using continuous slope mass rating along the Kanti Rajpath from Timpani Vanjan to Sor Vanjan. And authored by Ujjwal Krishna Raj Raghuvamshi and Ravi Kumar Dahal. And this paper will be presented by Ujjwal Krishna Raghuvamshi.
And today I would like to first of all thank our respected teacher Dr. Kathmandu Nepal for giving this opportunity when in the last time. And the topic of my presentation today is the slope stability analysis using slope mass rating along the Kanti Rajpath from Timpani Vanjan to Khor Vanjan. Actually, these are my just fresh data recently I have collected, and Actually, recently, this is on the process. Still, there is some failures, and that's why I've tried to do some numeric calculations on the slope mass rating, location and accessibility, objective, materials and methodology, results and discussion and conclusion. And as we know, first for the rock mass classification, we must use the Barton's Q system and Piniowski's rock mass rating system. But this is mostly very useful for the tunnel, but for regarding the slope condition, besides these rock mass conditions, in stability, and that's why this slope mass rating system is required. And there are many persons who have done the research on these topics, but I'm following Romana of the school from Spain. His research done in 1985, and which proposed the concept of rock mass, introduced some adjustment factor to basic RMR value to characterize the slope mass, known as slope mass rating. Among the geomechanical classification, rock mass rating and slope mass rating had got wide acceptance through the parameters in RMR, and the adjustment factor in SMR of Romana are discrete and are decision based. RMR is independent of SMR, but is a major component of SMR calculation. The continuous slope mass rating of tumors is somewhat less decision based and allow unique value of each adjustment factor and resulting into accurate value of final SMR. And regarding the location, this is the alignment of the Kantira spot from the near to the Maishpala up to this Baba area. Actually, I plan to do my analysis up to Purbanjan, but due to lack of time, I couldn't complete. But I've taken one sample from here and one sample nearby where there is big landslides, and one sample near to Sapedi, and one sample from this Bakwa area. Means there is a variation of the rock types from the phyllite to the granite and to the meta-sandstone, and based on the geometry in relation with the disponibility, what is the scenario we'll see here. And this is the location. It's located all along the Lalitpur and some part in the Makwanpur, in the boundary. And what I've found is that how the scenario is changing in this same place. In 2019, there was just a small landslide in the granite terrain. But as time passed, I have done this satellite image time series analysis to 2024, but just presented 2 years. This is the same location of this landslide, and regarding the present study, the geological unit are located from this Tistun formation, and in Tistun formation there are 3 samples were studied, and in this granite terrain of the epigranite, and another one is this Kalita formation, meta-sandstone. The study is done, and as I already mentioned, that beside the analysis in the different types of software, there are regular landslides, and the present scenario is bigger than this condition. This is 1.5 years back photo. And another thing, this area is also the zone with the high precipitation. Like in this zone, there is a precipitation of more than 600 millimeter per year. And now let's come to the main point, slope mass rating. And regarding slope mass rating is a slope stability system of classification. It is developed by Romana, as a modification of university's rock mass rating. It is an important approach to assess the engineering behavior of the rock slope. And it describes strength of an individual rock outcrop slopes. Nowadays, SMR is included in the most of the educational program and the technical studies in geological and civil engineering as well. Basically, as we all know that for slope mass rating, what another factors are used are the in basic rock mass rating, these factors F1, F2, F3 and F4. These extra factors are in this, and the slope mass rating is calculated by subtracting factorial adjustment factor of the joint slope relationships F1, F2, F3, and also an ADL factor depending on method of excavation. Means this F1, F2, F3 are the factors which is drawn by the orientation of the discontinuities in relation with the slopes, and where it shows F1 depends on the parallelism between joint and slope for a strike. If the strike and the bedding are parallel, like that, and its value range from 0.15 to 1, means 0.15 in case when angle between the joint plane and the slope face is more than 30 degrees, and the failure probability is very low, and 1 in case when both are near parallel. Means this is the condition of planar failure, and similarly in F2 is related to joint angle in the planar failure mode. Means how much is the joint deep angle of the rock beds. It is value range also is from 0.15 to 1, and in case when deep of the joint is less than 20 degrees, 0.15, and when it is more than 45 degrees, it's 1. For toppling mode of failure, F3 means equal to 1. And F3 refers to the relationship between the slope face strike and joint deep angle. Slope face strike and what is the joint deep angle is relation. And its value ranges from 0 to minus 60. And F1, F2, F3 are adjustment factors related to joint orientation. And besides that, how the slope is affected. Is this the natural slope, or just big splitting is done, or just normal blasting, or some heavy blasting is done? Depending upon that, so this slope mass rating value is affected, and it is given like this: for natural slope plus 15, this splitting plus 10, smooth blasting plus 8, blasting of mechanical 0, and deficient blasting minus 8. And this is also the correction parameter for SMR given by the Romana, as it's mentioned before. Let's go to the site conditions. First of all, I've started from the Paisikola area where there is a slide occurring, and at that location, what is found, mostly we can see this attitude of the bed to be this, and the slope to be this, and its RMR value is this, but after adjusting, it came the basic RMR to be 26. This is the plot done in Deep 7. What type of the failures are occurring, and let's come to this. In slope mass rating, I've done this analysis. The basic RMR is taken is calculated to be 26, but based on this slope orientation and discontinuity orientation, these factors came that we have mentioned F1, F2, F3, and F4, and based on that, it is considered that during the road construction, it is big splitting is done for that, because blasting is not done here, and its discrete SMR value is found to be 35, and continuous SMR value is found to be 36. This is as per the formula. It came like this. And finally, what is the condition? I think it's a little bit broad, sorry for that. And based on that, it is it can be said that at this rock condition in that particular slope, that condition is the bad condition, and with the stability is unstable, and failure condition with relation to this bedding and this major discontinuity, there is possibility of planar and big wedge failure. And after that, another location is this the Kathmandu location, and at this location also this analysis is done. Slope mass rating is calculated.
You have 3 minutes to.
Okay, I'll finish on that. As in the previous condition, we have seen that there is a possibility of the planar failure and wedge failure, but whereas here in this Kathmandu area also, the rock mass rating, basic rock mass rating is found to be 19, and the final slope mass rating is found to be 21. And in this condition also, there is a possibility of planar and big wedges, like here. Its uniaxial compressive strength is also not so good. RPB is also less, and spacing is measured at the side. Graph. What we can see is these 2 figures shows this is the direction, deep direction of the discontinuity, and this is the deep direction of the slope, and this shows the amount, means slope is dipping here and our discontinuity is dipping inside. So as it has the higher value, like this 70 degree, and slope has this, and it shows from the plan to the section. And in this type also there is a possibility of planar and wedge failure. And after that, another study was done near the Chapeli, where the rock type is the granite, and there is this analysis was done. In this slope, in this area, I have also taken the sample and some tests were also done. This is from the Chapeli area, and this is from the Jasurkola area, where the granite has the fine very coarse grained inhomogeneous grain size and mineralogy, variable mineralogy with slight durability, density, and these are the point of interest values. Similarly, this portrait of the character formation, it is very fine grained, and this last one. And what I'm going to show is that in the same, I have not got the proper time for showing, but in this same location, when there is prediction in the orientation of the hill slope for the particular rock mass rating, similar rock mass rating also, there was a variable slope mass rating value I found. Like this here, there is a possibility of planar and wedge failure, and this slope mass rating is slightly upgrading. And after this, we can see in some locations the slopes are stable, but nearby this another location there is a big slide. This because due to the relation of the discontinuity with that of the slope, that's why how this discontinuity relations also affect in the slope stability so clearly. This is also the photo of the Chapeli area. And finally, I've done one analysis in the successful area that is just in the Maganpur area. Here, this RMR value is also higher with very good progressive strength, and its data are like this, spacings, images like this. But here, in this area, the slope is very higher, more than 120 or 150 meters, but it is still stable. And this is due to its material properties as well as the orientation of the discontinuity in relation with that of the slope. Here also, the basic RMR value is 40 and the SMR value is 6. But besides the previous analysis, here is a possibility of some joints or many wedges, and this is normal condition. In previous flow condition there was bad condition, but in this, as just from the calculation, this and this is the summary of that analysis. We can see here all here bad condition, bad condition, bad condition, and bad condition, but this is in the normal condition. Depending upon the rock, how the rock mass rating, besides the rock mass rating based on the discontinuity orientation, is stable, and this is the conclusion. And the main advantage of this methodology is the possibility to use for easily calculating the correction parameters of SMR in case where all the slopes have the same tip and different type as in linear infrastructure and open pit mining. Another significant improvement of this methodology is the possibility of working with the field measurement of all discontinuities of the poles of the intersection lines with flows in order to determine the distribution of correction parameters. Thank you.
Thank you, Mr. Raghu. Since we have run out of time, we'll just take one more question. Only one question. So you have utilized the SMR for the support. SMR. After implementing the recommended support.
Yes. These factors like slope mass rating, or like I've also done the analysis in depth. What is the possibility? Is there the possibility of wedge failures? I've also calculated what is the percentage of the wedge failure, planar failure, or coupling failure, and based on that, we will be using this for the slope stability definitely, because how much depth of the rock walls is needed, or what type of structures are needed. Based on that, we can decide. Thank you for this question.
Okay, thank you. Starting from the very interesting top PhD topics related to the railway was not done, was Young's modulus and slope stability analysis, and then of course the DGPS, and then DGPS, no, DGSP, and of course the GBM. This type of papers were presented, and all are very applied in the Nepalese context. So all these papers are relevant, and I request all the authors and co-authors to please make some manuscript out of this and publish these papers. This should be, of course, interesting to our community, and of course not only the geologists, also the communities who are involved in this type of work. So that's my request, and on behalf of our team, co-chair Mr. Amar Chong, and then Rapporteur Jaya Singh. So I'd like to thank you all for your presence and patience. Thank you so much.
To provide token of appreciation to our chair, co-chair, and rapporteur of this technical session.